Okay, good morning, everyone. Now, your homework for Chapter 27 is due on Wednesday. I will finish Chapter 27 today. We're mostly finished. We're just going to get a little bit farther with talking about resistance and conductivity today. But I want to go back, first of all, to where we were last day. We were looking at a capacitor that was discharging when a wire was connected between the two plates. Now, last class, when I drew the wire, I didn't draw anything on the wire, just a wire itself. So that would draw in a sense, a huge amount of current, or the current would dissipate very, very quickly. Now what I've done is I've put some light bulbs, A and B, on the circuit, and A is really close to the negative plate, B is going to be farther away. So we want to think about here, which of the following factors is going to make A light before B? And just as a way of review, how does the current flow through the wire? What causes the current to flow through the wire? Yes?
The voltage of the capacitor.
Okay, the voltage
difference between plates.
But in that, let's say, for instance, down here, the wire doesn't, how does the wire know anything about the capacitor? Is really what I'm asking. Yes?
The fringe field from the plates. So
the fringe field kind of starts the flow. And then, why does the flow continue after that? Yes?
Because as the fringe field pushes to distributes the charge, the charges start being attracted to each other on the wire, so that the electrons want to follow the positive charge that gets distributed about the right side of the wire instead of follow it around.
Okay, so there's some distribution of charge. Yes?
To tie into that, there's a greater charge density closer to the capacitor plates, and there's less near where the switch is closed, because that's where since it's going to be positive one side, negative on the other side, they're going to start neutralized. That will cause a electric field to form, and electric field would cause current to form.
Okay, so very good, everyone. So let's just summarize that all together. The fringe field is kind of like the mechanism which starts the flow of charge. And then there needs to be some non-uniform distribution of charge along the surface of the wire, which acts like a field guide for electric field lines. So when current is flowing, the wire is the conductor, is not in equilibrium. Right? It's not in equilibrium. That's what causes charge to want to move. the capacitor is what keeps it at equilibrium. Now obviously that doesn't continue forever because the capacitor loses its charge. It can't keep pushing the charge forever. So in the following scenario, let's imagine that, well, we don't have to imagine it's the picture here, but bulb A is connected directly to the negative plate. Number two, let's imagine that bulb A actually burns brighter. And number three, actually, I'll just keep those two. So which of those two factors might cause bulb A to light before bulb E? The fact that A is closer to the negative plate, or the fact that A burns brighter? So I want you to explain so we'll take a quick vote here for, first of all, number one. Take a moment to prepare your vote. So does the fact that A is connected directly to the negative plate, does that factor cause A to light before B? Yes, no, or we need more information. So prepare your vote. And let's take a vote here. Okay, was there a question at the back? Or that's a 1? That's a 1 or an A? All right, A, okay. All right, so take a moment to convince your neighbor as to what the correct answer here. The important thing is the explanation. All right, get ready to prepare your vote. So does the fact that bulb A is connected directly to the negative plate cause it to light sooner? And show your vote on 3, 2, 1. Okay, we have sort of a cluster of greens on this side for B, and then a cluster of reds with some greens kind of over there. It's kind of 50-50. There's a few more info, but it's kind of 50-50 between the two here. All right, so let's try to think about this here. Some ideas. How would we figure this? Just kind of thinking about what we know about circuits so far. Yes?
I kind of thought of it going back to like the analogy that like the wire's like a hose, but it's a hose like that already has water in it. So like there's already electrons all throughout the wire, so when you connect it, they all start moving. And like it doesn't just start at the negative plate and go to a positive plate. Like the entire, like all the electrons in it start to shift. So like the current is in like all parts of the wire. It doesn't just start at one end and loop to the other.
Okay, so in a sense you're saying all the electrons, since the wire is like a pipe full of water, they all kind of start to move simultaneously as soon as the negative plate starts to push. Another comment?
Yeah, I think you can also think about light bulbs very much when they're incandescent light up because electrons are bouncing off the ions in them, and that causes thermal energy, which eventually causes a glow. So if it if it's burning brighter, that means it for the same current.
So we're still looking at number one.
You can like do it by ruling out the other one, right?
So right now we're just looking at this one though. We're not considering the fact that it's burning brighter or not. But hold that thought. Let's come back to that in a moment. All right. So now, so the answer is no. It is no for number one, right? Just because of the wire's like a pipe full of electrons. Now, one of the assumptions we're making here is that this fluid, or this sea of electrons, the sea of conduction electrons, is incompressible, right? Now, in reality, what happens is when you close the switch, there's going to be a wave that propagates very, very quickly, kind of like a ripple in electric field. Imagine if I shake a rope and that pulse travels through it, basically turns it on. But that's almost instantaneous. Why does a light bulb glow to begin with? Well, it takes a certain amount of time for it to heat up. So since those time scales are very, very small, for all practical purposes, we see them light at exactly the same time. Right? And yes?
So it is technically yes, but it's just such a small time that we say it's no.
Well, the other time factor is that it takes time for the filament to heat up. So the reality is that for the signal to reach A versus the signal to reach B, it's happening, that time scale is orders of magnitude smaller than the time scale it takes for the filament itself to heat up. But it looks instantaneous, both of them. All right, what about if bulb A actually burned brighter? So A is a brighter light bulb than bulb B. Would that cause A to light before B? So take a moment to prepare your vote. I'll take a question.
Yeah, the question about the first one. What
Yeah.
if the distance between A and B was like really, really large? Then what if it be not?
If the distance was really, really large, well, now there are some practical, so that is, let's say that this wire was, a mile long or something like this. So B is just really, really far away, right? And this gets into the whole question of long-range power transmission. But there is something called signal loss, right? Where there is now. This is something we'll talk about next. I'm glad you raised this question here. But for the purpose of a small kind of contained circuit, we consider these wires right here to be ideal. So this we consider to be an ideal conductor, and meaning there's no dissipation in these wires themselves. Only dissipation occurs in the light bulbs themselves. But in practice, if you have a really, really long wire, right, your resistivity will increase. And we'll see that explicitly in a moment. So that's a very good point. If you have a really long wire, that's going to change things. So this might not be the most practical way to transmit power long range, just to have a really, really long wire connected to a capacitor. All right, so now for bulb A, let's take a moment, prepare your vote. And is the fact that it burns brighter going to cause it to light before B? And we'll vote on 3 here. Had a moment to think about it. 3, 2, 1. Let's see your votes. Okay, 30 seconds. Convince your neighbor. Explain. Did anyone change their mind? I'll give you, get ready to prepare your vote. And on 3, 2, 1. All right, majority says B, which again is correct, it's no. The fact that A is burning brighter, what does that mean practically? Yes, John?
A higher resistance?
It has a higher resistivity, so it's dissipating more electrical energy into thermal energy. That's happening at a quicker rate in bulk A than bulk B. But if you have a hose, right, and you have a small, if you poke a hole in it, a big hole here and a small hole here, when you turn it on though, the signal is going to it's going to be moving past them at the same point, in a sense. One way to kind of think about it here. Yes?
So would B net for A, or is it the same net?
Can you repeat the question?
So since A doesn't light first, would B light first, or they both light at the
Same time.
Okay.
Same time. And again, this is for normal kind of scales within a building or something like that. Wouldn't be from town to town, or from power generation station to a transformer or something like this. Yes?
Why wouldn't light bulb A's higher resistance cause it to start glowing before light bulb B?
All right. Can anyone answer that question? Why does the fact that A has a higher resistance not cause it to start glowing before B? The simple answer is this, is resistors don't use current, they dissipate electrical energy. So it doesn't change the flow rate. So current is just the rate of flow of charge. So let's review that from so I wanted to touch on this from last class, just a few of the concepts that we had. We had drift velocity. These are the main concepts from the chapter. Drift velocity, which we wrote down an expression, E tau over m, multiplied by the electric field. So the electric field is what pushes the charge, causes it to move. This drift velocity is an average speed, right? You need to have a certain amount of charge. Tau is the average time between collisions, and m is the mass. That would be a model for how the electrons bump their way through a lattice of positive ions, which that lattice itself is not static. It can be kind of vibrating. The electrons, that sea of electrons, though, is tumbling through. All right, so then we had electron current. And electron current is really the number of electrons that are passing a given point in your wire per unit time. So this is going to depend on the number density, right? How many conduction electrons are actually available to move. It's going to depend on the area, cross-sectional area of the wire, and then how fast they're moving, just the drift velocity. So electron current. Then we had regular current. And if electron current is the number of electrons that pass a point per given time, regular current is the amount of charge that passes per unit time. So this one is really number per unit time, and current is really the amount of charge Q per unit time. And N and Q, big Q, are related to each other just by a factor of the charge itself that is moving. So the total current in a conductor would be just little e multiplied by this, or little e n sub e a VD. Right, and then we define something called current density. Because I could imagine a wire that's a very thin wire carrying a large amount of current, right? Or a thick wire, the current could be exactly the same, right? But its density would be much less because it has more area over which to distribute. So the current density J is just the total current divided by the area. So this is E, N sub E, VD. And we wrote this last class as J equals sigma times E, where sigma is N sub E, E squared, tau over M. This is called the conductivity. With units, ohms to the -1, meters to the -1. So what is conductivity really a measure of? Well, conductivity is really a measure of how eager electrons are to move in response to an electric field. So if you have electrons that are really eager to move in response to an electric field, you're going to have a high conductivity. What are some things that affect this conductivity right here? Well, obviously the lattice structure. Right? If the lattice structure is really compact, it's going to be harder for the electrons to bump their way through that lattice structure. Impurities in the lattice itself. If you have giant, big impure scattering centers, that's going to be harder for the electrons to make it through. And then temperature as well. Temperature increases the effective size of the lattice by causing it to vibrate more vigorously. All right, now there's a quantity here that's related to conductivity called resistivity, and that's what we'll talk about next. Question?
Relating conductivity to drift velocity, is one of those dependent on the other, or are they just both dependent on E, M, and tau? So like if I increase the conductivity of a material, would the drift velocity also increase because of that?
If you increase the conductivity of a material, will the drift velocity increase as well? Let me think about that. It's a good question. So let's see. So the drift velocity here, we could imagine that, what's the drift velocity in a material if you have no electric field? Well, the conduction electrons are kind of bumping around still because they're at a finite temperature. They're still moving around, but they don't tend to drift any one particular direction. That's what the electric field does. Now, the conductivity is a property of the material whether or not you have current or not. Okay, so it has a certain conductivity, which is a property simply of, well, how many electrons do we have that can move, that are mobile charge carriers? What's their charge, time between collisions, and mass? Yes?
Is tau also a property of the material?
It's a property of the material. And it's also going to be affected by things such as lattice structure, impurity, and temperature. That's why, so sigma is a function of those things, and that's really built into these parameters, right? Tau, for example. All right, good questions. Now let's look at, so resistivity we define to be just the reciprocal of conductivity. So resistivity the Greek letter rho is 1 over sigma, or 1 over the conductivity. And this has units of ohms, meters. So not the same, you might be familiar with resistance. Resistivity is a little bit different. And I'll kind of connect them here in a moment to tell you how they connect to each other. But resistivity is a measure of how reluctant electrons are to move in response to an electric field. So let's zoom in to a small section of a resistor. And by the way, all conductors, all real conductors are really resistors. Okay, but for instance, copper has a much higher conductivity than carbon. So what we would say, well, in fact, it's several orders of magnitude. What we would say is when I'm talking about a resistor, I'm just talking about something that has a really low conductivity compared to, for instance, carbon compared to copper. So if I draw a small section of the wire, and I'll take my wire to have circular cross-section. Remember, what causes the current to flow is a non-uniform distribution of surface charge. So we might have something that looks like this. The surface charge is non-uniform. Non-uniform surface charge drives the flow of current. So I have an electric field in my wire that looks like this. Now let's say the wire has length L. So the current in the wire let's try to relate the current here to the resistivity. The current is just going to be the current density multiplied by the area. And J is just equal to sigma E A. And sigma we can write as 1 over rho. So let's just write this as, we're going to have a rho on the bottom and A on the top. And then E, I'm going to write as delta V over L. So delta V is the voltage difference across this chunk of resistor. There's a voltage difference across this chunk of resistor. And we'll say it's kind of like, we'll say the electric field in this chunk of resistor is uniform, which is a good assumption to make if it's uniformly, if the material is uniform. Just a constant electric field. All right, so let's just write this then as A over rho L delta V. So this equals I. Now everything in the bracket right here, I'm going to call 1 over R. All right, so rewriting this, then I get I equals delta V over R. Ohm's law, written another way, where R, resistance, is rho L over A. Okay, now Ohm's law is not a law of physics that's always true for all materials. It's a model that works well for ohmic material. And what do we mean by ohmic material? Well, materials, and a lot of materials where current and voltage are proportional to each other. But that's not true for all materials. And in practice, in most materials, if you have too much current or too much voltage, it's not going to be ohmic anymore. Which really what that means is its resistivity is a function of temperature. So, now, last class I gave you an example of what that might actually look like. So, I have a simple circuit with a light bulb, and then up here there's a tungsten filament. Now, if I push the switch, the light bulb lights. But if I was to change the amount of resistance in the circuit by heating the filament, the light bulb gets really, really dim, right? And then as the filament cools, that light bulb gets brighter and brighter. So what's happening as I add temperature to the tungsten filament right there is I'm changing its resistance. Okay? Its resistance. How am I changing its resistance? Well, I'm changing it by changing its resistivity. Its resistivity, which is related to the conductivity. And you see the conductivity is going to depend on things like collision time. Right? So if I heat it up, are collisions going to happen more frequently or less frequently? Yeah, the lattice is vibrating around more violently. There's more frequent collisions. Now, let's look at some other factors here that change the resistance. One thing I'll say about resistivity is that it's just a property of the material itself. Okay? Resistivity can be a function of temperature. Now, resistance is a geometric property, just like capacitance. Resistance depends on the length of the filament and its cross-sectional area. If you'll notice, and I'll pass this around just so you can take a look at the filament here. You'll notice that the filament is really tightly coiled. So it's very, very long. It has a very, very high resistance because it's very, very long. It's just coiled. And then the area is really, really small as well. It's very, very thin. That gives you a high resistance. Right? Which kind of makes sense if you were to think about what would be the impedance to water flowing through a pipe while you want to make the hose really, really long and really, really narrow. That would make it harder to push water through the hose. So same thing with resistance. Well, analogously. Now we are assuming here that electron, the sea of electrons, are not compressible. Water is very incompressible. It would be an incompressible fluid. All right, so I have a picture here which will help us with this a little bit. So here is resistance, which depends on these three factors, rho, L, and A. If I can increase the length of the resistor, that would increase its resistance. I can increase the area of the resistor, that will also increase its resistance. The other thing that increases it is the resistivity, and which is illustrated here by the number of scattering centers. So as I increase the resistivity of the material, the resistance grows. It's harder for those electrons to flow, to move through, because there's more places through which they can scatter. Now, if I take a resistor and I connect it into a circuit where I have Ohm's law, V equals I times R. Now, the bottom box, the red box at the bottom, that's really, so this one right here, that's really the resistor. And then this is the voltage source, or the battery. All right, now you can see right now there's 9 milliamps of current that are flowing. Now when you're thinking about a circuit, this would be the simplest circuit we could build. But what you want to think is globally. So if I want to push more current through the circuit, I would have to increase the amount that I'm pushing. So think of a battery as what's doing the pushing. So I increased the voltage of the battery. Now I'm a little bit over 6, about 7 volts. that'll increase the amount of current to 14 milliamps. But if I also increase the resistance, that's going to cause the current to decrease 10.2 milliamps down to 9.6. So it's kind of limiting. The job of a battery is to provide a source of constant electric potential. And if I had no resistance, your circuit would draw ideally an infinite amount of current. Or that would cause the water to get, or that would cause the wire to get really hot, right, and start to glow. But this is sort of limiting the amount of current that's actually flowing through. All right. So let's look at an example here. And we're going to start this class. We'll finish it next class. But I'm going to pass out a sheet of paper here. And this is free. There's a typo on the front. You're not going to hand this sheet in. You're going to keep this. So once you get this sheet right here, what I want you to do is I just want you to read demonstration number 1, and I want you to fill out the graph. There should be a few extras floating around the back. Just raise your hand if you don't get one, and I'll make sure. And then you'll want to circulate those around. All right, does everyone have a copy? There should be some extras over here. Yeah, just raise your hand if you don't have one, and we'll get one over to you there. So as that's going around, so demonstration number 1, I want you to sketch what's called the current voltage characteristics. So I want you to sketch a resistor. It's kind of like, it's similar to this simulation here in that the voltage source is variable. So let's, you can change the voltage. Up or down. So what does that curve look like? So individually, I want you to sketch your prediction. Technically, so what we're doing is we're defining a resistor to be one that obeys Ohm's law. Okay, compare your prediction with your neighbor.
I'm thinking it would just walk straight. Increase the
Just don't know the slope of the line.
The current will also
But I think we're assuming delta. We just don't know what. 480. So that would just be I mean, I could be wrong, but it should
All right, can someone describe what the graph would look like in this case? Yes. Linear, positive slope or negative slope?
Positive.
And how do you know it's linear?
Equals IR.
Now, what does the slope represent in this graph? So if we were to try to interpret, if we were to, experimentally, we plugged in some resistor device, kind of like this circuit right here, unknown resistor, and we're just changing this right here, and then we're measuring the current. Okay? But let's say we don't know the resistance of this. What would the slope represent here? 1 over R, right? Yeah. It's just 1 over the resistance. All right, now, so for number 2, let's move on to number 2 now. Talking about a light bulb. The resistance of conductors increases as the temperature increases. As more current flows through the filament of a light bulb, the temperature of the filament gets higher. So if I connect a light bulb filament to a variable, let's say this resistor now is a light bulb filament, I want you to sketch the same graph, I versus V, for a light bulb filament. And I want you to work on this individually. To sketch your prediction, okay, compare your prediction with your neighbor, explain, and you also want to answer those questions about whether or not the light bulb obeys Ohm's law, and how would you find the resistance of the light bulb.
It's a resistor that heats
So yeah, it's slow. It would be just the increasing voltage or increasing.
Okay, can someone describe what would the graph look like in this case? What are some features of the graph that you have sketched? Predictions? Yes.
It kind of goes like this. Like it increases quickly at the beginning and then it kind of tapers off.
So it kind of goes, you're saying something kind of like this?
Yeah.
Now, what does it do when it's up here?
Flat.
Does it go completely flat?
I don't think there's ever really like a hard cap, right?
So it just would. All right, now, why does it bend to begin with? Let me make that more. And does it keep bending? So it bends, and then does it keep bending? Well, why does it bend, and then does it keep bending, is the question? Yes?
It bends because as the current increases, that would increase the temperature, and therefore would increase resistivity. So like you wouldn't be able to reach a higher and higher current.
Okay, so what you're saying is current is caused by an electric potential difference. As the electric potential difference increases, you increase the current, but simultaneously the resistance is also increasing because it's a function of temperature. So it's not just increasing proportional to anymore. Yes?
Is it kind of like, so the slope is 1 over r, and 1 over r is increasing. So would it be kind of like a logarithmic graph? Because the slope of a logarithmic graph is kind of like 1 over x? Or does r increase linearly with temperature or faster than that?
So exactly how does resistance depend on temperature is what you're asking. Okay. Now, so there's a couple questions here. Any other questions first before we conclude the discussion of this? Yes.
Does it curve and then level off like
Flat?
horizontally?
What would a flat curve mean about the resistance?
That it's equal to the rate of that voltage is changing?
So are you talking about a a horizontal line?
Yeah.
So if it was a horizontal line, what would be the slope? What would be the resistance?
It would be changing at the same rate as voltage. Right?
What would be?
The resistance would be changing.
It'd be infinity, right? Well, there'd be infinite resistance, which would technically mean it's no current at that point. Now that would be pretty. Now we wouldn't want that in a filament. You know, its resistance should increase with temperature, but we would want it to reach sort of an operating temperature where, you know, it heats up, meaning its slope decreases. This just means the resistance increases. Right, the light bulb begins to dissipate more and more energy. Now it's electric potential energy that's being converted to thermal energy in the resistor. If it's a filament, if it's an incandescent filament, it's some thermal energy, it's some light energy as well. But that resistance should reach some kind of a constant operating temperature, or some kind of an equilibrium, where the slope, after a while, becomes constant slope. The operating temperature for a filament would have to be several thousand Kelvin, right? Which is why you would put a filament inside a evacuated or a high fidelity vacuum, right? So that that hot material doesn't burn up or doesn't become oxidized. They're very hot. You don't want the filament to light on fire and then break apart from the electrodes, right? So now that constant slope, meaning you've kind of reached some temperature where it's just not getting hot anymore. That just is meaning the input temperature, the input energy that it's receiving, it's converting all of that to thermal energy and light energy at the same rate that it's receiving electrical energy. Yes.
So why is it not horizontal?
Horizontal would be infinite slope. Or sorry, horizontal line would be infinite resistance. Right? Infinite resistance would mean the light bulb actually goes up. So if this case was not, if there's not a vacuum around the filament and the filament lit on fire, right, and it's severed, then in a sense it becomes infinite resistance because the wires aren't connected to each other anymore. It just, you know, it literally burns the filament. So in a sense, then your current, then it would kind of go back down to zero. You have no current, or regardless of what voltage you have at that point. Yes?
And what's confusing me is that it says voltage is also increasing. So voltage is increasing at the same rate as the resistance. Does it not go to zero then?
So if I keep adding more, now, all right, so a real resistor, and one question here as well.
Well, I was just going to say, so basically, so the reason that the current keeps increasing is because the resistor is able to dissipate that energy and not increase the resistance. Like it gets rid of the light energy so that it doesn't vibrate faster. And so the resistance stays constant at a certain point on.
Right, but now, so a real resistor is going to have a limit to it. You're going to reach a limit where at a certain point, if you apply too much voltage, eventually you're going to burn out that bulb. Right? Now let me show you a picture here, and we'll end on this, which will kind of help this make a little bit more sense. If I think of a resistance this way, where the battery is pushing on, this would be the positive side of the battery, this would be the negative side. So the battery is causing negatives to drift from the positive to the negative side. It's acting like a pump, it's pushing the charge. Now, you can see those charges in this simple model here, they move kind of freely through this ideal wire. And again, we're only moving at fractions of a millimeter per second, right? But the reason why you can have large currents is because you have so many of them that are moving. But they're not moving very fast, any individual charge. Right? So that number density is really important when we're talking about current. And then you can see when they enter the resistor, they start to interact with the lattice of the resistor and they start to feel some kind of resistance. So here's the drift velocity kind of illustrated, where the electrons, you can see they're not moving at a constant speed, they're being bumped back and forth as they go around. Now what happens if I increase the resistance is basically I've changed the lattice structure. The current goes down because it's harder for the electrons to make it through. Other things that I could do is I could increase how much the battery is pushing. Right? If I increase how much the battery is pushing, what that does is it causes the resistor to get hot. Right now that lattice is vibrating so vigorously that it might actually start to glow. Right? And with a high enough resistance, or if I make it a low enough resistance, I can get a larger and larger current. Right? So it can get white hot, and we have light. All right, so we will pick up with this on Wednesday. We'll continue with number 4. Okay, so I have
I got my hands by
Because the lower resistance, that's kind of what came to my mind. I feel like I asked a lot of questions. That's right.
Yeah.
So lower resistance would actually heat it up more?
lower resistance would what?
Heat it up more. It would, because I saw it go.
Yeah,
Hotter
yeah.
as low resistance.
Why?
I don't know. Because there's more current through it.
More current. Yeah. So, and this is what we'll come to next day, but the power that's dissipated in the resistor, power is just energy per unit time. Voltage is joules per coulomb. Voltage is joules per coulomb. And if I multiply joules per coulomb, by current, current is just coulombs per second. I get power, joules per second. So there's more power for a given amount of voltage, which is set by the battery. If I decrease the resistance, I increase the amount of current that's drawn, and more power being dissipated in the resistor. So battery is a source of constant electric potential, but the current will depend on the load or the impedance that's connected to that battery.
I have a question about the homework, actually.
Yeah, so we can ask right now. I also have office hours right now as well.
Oh, you lost it.
Yeah. Yeah, I'm going to head over there right now, so that works as well.